Up here we have the source area. So we had the earthquake, we had all the rocks coming out of the source area. The source area is the steep basalt cliffs. And as the rocks came out in all directions, they would have hit the bottom of the cliff, the ground there. And as they leave the cliff face, they're in free fall, they hit the ground and they start to roll and bounce. And this is an impact crater. And this impact crater is about 20% of the total area of the boulder. So this is the bounce here, and it's about 5 meters from here to the hedge, and it clipped the hedge completely about 2 meters above ground level. This is an impact mark from the boulder that came through the fence. There's the second impact mark, and then it went straight through the garage. And you can see the hole in the roof there, and the boulder is actually sitting in the garage at the front of the house.
The purpose of this work is to try and understand better what areas of Christchurch are likely to be impacted in the future from rockfall. And this is important because of the rebuilding and reconstruction activities that are being carried out at the moment. The reason Christchurch, or the Porthills of Christchurch, are susceptible to rockfall is because they're built on an old extinct volcano, and you have a series of quite steep rock slopes which are essentially lava flows, and these bluffs are susceptible to rockfall, as we've seen from the recent earthquake. So Castle Rock is obviously a Christchurch landmark. Climbers use it, walkers go past it, everybody can see it who's working in the area. It's a beautiful part of the landscape. Unfortunately, Castle Rock was given quite a big shake during the earthquake, and there was a lot of boulders and rock loosened, and a lot of rock fell off and went down the slope. So we're on Castle Rock, and we've been observing and videoing the scaling work that's been going on at Castle Rock. But this gives us a brilliant opportunity to kind of look at what the rockfalls did during the earthquake, because we are throwing the rockfalls from the same locations that they sourced from during the earthquake. And by videoing these, we can understand things such as how high do they bounce, how what the rotation is, so their angular momentum as they're going down the slope. And all this is really important, because you can imagine if you're building a rockfall fence, you want to make sure that your fence is high enough for the boulders. And so what this does is allow us to calibrate the numerical models that will need to be done for design purposes, but also to give us an understanding of just what happened during the earthquake. And that's a really, really important aspect. And we're quite lucky to be able to do this, so we can actually calibrate these models. So at the top of the cliff, we're using bars and other various mechanical methods to actually prise these loose boulders off. And as they start to move, the boulders essentially free fall, and they go from the source area, they fall, and their first impact is either on the rock face on the way down, or they impact the kind of talus or area of rockfall debris at the toe of the slope. Once they hit that, they can do one of two things. They can either slide, and if they slide, they don't tend to go very far. But if they start to roll, they then start to accelerate, they start to pick up momentum, and they start to increase their velocity. And these are the boulders that worry us, because these are the ones that travel many hundreds of meters down the slope. And these are the ones that have impacted housing in the Porthills areas as a result of the earthquake. As the boulders travel down the slope, rolling and bouncing, and they tend to impact other boulders or other bits of rock that are along the slope, and they can shatter into like 3, 4, 10 or more pieces, like a shotgun effect. And all those boulders can then, much smaller boulders, can then continue to roll down slope. And we're using a GPS to try and understand the spread of the boulders from the one source area. They hit an area of ground that deflects them into a different direction of movement. And so what we're finding is that these deflections may be plus or minus about 30 degrees from the center for the average fall line. These yellow lines here represent the trajectories of the mapped rockfalls. And so you can see there's trajectories all through here. This is Heathcote Valley, and this is over in Littleton. And the red circles are actual mapped boulder endpoints. So this is the source area, and this is where they've gone to. And this is kind of the product of what we're doing. We're trying to delineate zones where rockfalls are probable or likely to impact. And so this is really the first stage of the risk assessment. What we then have to do is start looking at what the probability of a boulder impacting a house or a road or other facility in these zones. And this is where we start getting into risk modelling. One of the critical factors now that we're doing is trying to back analyse and understand what controls the rockfall and what controls the kind of the trajectories of the rockfall, and how that can be used, that information can be used to start facilitating a better understanding for reconstruction works. You know, we don't want to build or allow people to build in areas that are prone to rockfall, but we have to quantify what the rockfall risk is. If the risk of being hit by a rockfall is way down the scale compared to walking across the road or from driving a car, then we need to know that.